Okay, so we've talked about our first business example. So now let's move into interpreting the second derivative from a graphical point of view. And I need more paper. Alright, so let's talk about interpreting the second derivative geometrically. First, let's just talk about what we know about the graph of a function already. So say we have some graph here and some function that's maybe goes up like this and then comes back around and flans out like that. Just looking at this function without its derivatives or anything like that, we can say where this graph is negative below the x-axis and where it is positive above the x-axis, right? So we can already say that. So if this is some function, so let's say f of t, the sine, alright, let's say f of x, so we'll say x, and this would be the output y, and there's the curve f of x. The sine of f of x tells us where the graph is above the x-axis, This is where f of x is positive, and where the graph is above the x-axis and where it is below the x-axis. Where f of x is negative. And we can tell that just by looking at the graph, saying right here and beyond to the left it's negative, and from here to the right it's positive. The sine, what am I going to say next? I've got the function, now I want to say the sine of its derivative, f prime of x, derivative of x. The sine of f prime of x tells us, what does that tell us? It tells us where the slope of the graph is tilted up, right? Positive slope. That's where f prime of x is positive, and where it is tilted down, that's where f prime, its first derivative, is negative. Okay, so we already know that. So if I drew a little picture of that on this graph here, I could say that for the first derivative, we've got here, okay, maybe not, there we go, a positive slope, positive slope, positive slope. It's all positive, right? And then here we have a zero slope, and then over here we have a negative slope, and then it kind of flans back out, negative, and then it looks like it becomes 0 again. So anytime we have a change of positive slope to negative slope, there has to be one of those 0 spots in between. And that's what that whole previous section was all about with the max and the min values, these flat points, right? Okay. What about the sine of the second derivative? What does that tell us? The sine of the second derivative tells us where the, how should I say, where the graph is curved up. That's where the first derivative is positive, and where it is curved down, where f prime of x is negative. So if I redraw this graph down here, it's roughly like this here, and then it levels out something like that. So where is the graph curved up and where is it curved down? Well, let me get a better pen. The graph is curved up here, right? That's curving up. It's curving up, same where we had a positive slope there, right? Positive slope, and we had a positive slope all the way until we got to that 0 point for the slope, which meant that our first derivative was positive. But look here, we have curving down here. We have a curving down behavior right here. We have a curving down behavior, and over here we're curving down. And then over here, we're starting maybe to curve back up, right? It's tilting, yes, it's going from pointing down, and it's starting to tilt back up. It's starting to tilt back up. Now, here, in between positive and negative derivatives, first derivatives, we had to have a 0 point. That's where the graph flattens out. Here, we've got a positive and negative second derivative, so there must be a 0 point in between, and there is, but what is happening at these 0 points? What is happening at these 0 points? There's no curve to the graph. For one moment in time, the graph is perfectly straight, just like that. Perfectly straight with no acceleration. Just like in that example with the car, at that one moment of time, right in the middle, it was traveling 15 meters per second, and its acceleration, second derivative, was 0. At that one moment in time, it was not speeding up, and it was not slowing down. And that's going to happen in between positive and negative second derivatives. We call this shape concave up. We say concave up. We call this shape concave down. So this would be positive concavity, or we could just say this part of the graph is concave up, then it becomes concave down, then it's concave up again. So positive concavity, or a positive second derivative corresponds to a concave up shape, and a negative second derivative corresponds to a concave down shape. So right here, this is still curved here. This is still curved. That's not a 0 point anymore for this, because this is a second derivative now. You actually can have spots in your graph where the first and second derivative, and many more derivatives, could all be 0, but that's, in this case, that's not happening there. Now, next thing. We call these 0 points, so continuing from here, we call the points where it changes from positive to negative concavity, or from negative to positive concavity. I'll say where f double prime of x is equal to 0, we call those points points of inflection. So for this shape, if I redraw this graph, that's a point of inflection there. I'll say POI for point of inflection, and there's one right there as well. Now you know, if we're taking derivatives and setting them equal to 0 and solving for points, that sounds very similar to finding max and mins of graphs, because that's exactly how you would find a point like this for the first derivative. You would take it, the derivative of the function, set it equal to 0, and that's going to tell you where that flat point is. Now, we have a new thing that we can do where we can find the second derivative, set it equal to 0, solve for x, and get that point where the graph has 0 acceleration, which definitely has applications in business and in physical applications as well. If you think about that example we did before with the acceleration of sales, that would have been useful for knowing when our sales leveled off, because somewhere in between these two functions we went from positive acceleration, 175 units per month squared, to a very large negative acceleration, which is bad, right? We're selling a lot less here. Somewhere in between there was a 0 acceleration point where we're no longer selling more. We went from positive to negative, so we're somewhere in between 10 and 30 months, there was a point where we started, where our sales leveled off when we're not selling any more games per month. We're not accelerating anymore. It's a little complicated with this problem because there were two functions, but still a very useful thing. Okay, let's do some examples. Oh, one more thing I can say about points of inflection. You can think of them as the steepest points of a graph. In terms of that acceleration problem with the car, that's its fastest spot. Where its acceleration is 0, it no longer has any time to speed up, no more time to speed up, and then it had to start slowing down. Its fastest point, at the steepest point of the graph, the fastest speed is going to be where that 0 point is for the acceleration. Okay, let's do some examples with pictures. Locate points of inflection and concavity. I'll just say it that way, just nice and quick. Okay. Let's say we have a graph like this. Ooh, that's ugly. Okay. First, let's identify the concavity. I'll go ahead and put the next one up. The points of concavity, where the concavity is positive and negative. So from looking at this picture, I see that I have this shape is supposed to be concave up, so that's going to be positive concavity. So this is positive concavity there, and this will be a negative concavity. So this is negative concavity, and this is positive concavity. Somewhere in between, there has to be a point of inflection, the steepest point of the graph. Now you could say, well, you know, what about this? This looks really steep, or this looks really steep. But these arrows imply that this curve keeps growing this way and possibly gets steeper, right? So we don't know. We would need more about this side of the graph. But this little arrow definitely implies that this function goes off to infinity like that and keeps getting steeper and steeper. So the steepest point of the graph, when I say the steepest point, I'm talking about points in between positive and negative concavities. Alright, and likewise there wouldn't be one over here as well. What about this second one? Well, I see positive concavity. It's slower than this concavity. This is a very fast acceleration, but this over here, it's still positive. It's not negative anywhere. There are no points of inflection. There are no points of inflection here because it doesn't change direction anywhere. It doesn't change. The curve doesn't change. The curve is always curving up. It doesn't turn and start going down. What about, so this is like an exponential graph. This is maybe like some cubic graph, like a cubic polynomial. This is like some exponential graph. So how about a logarithm graph? This would be some kind of logarithm graph. Well, this is kind of similar to that, except that it's all negative, and there are no points of inflection. No points of inflection, and it's always curving down. It's always curving down. Slope is positive everywhere. Slope is always positive, but we're not talking about slope here. We're talking about concavity. So all of this concavity is is negative. Okay. How about this graph? Well, we have concave down here. This is curving down, so this is a negative concavity. Then we have positive concavity. It turns around, starts curving up, and then it curves down again, so negative concavity. So that means here and here somewhere there are going to be points of inflection. Now, I can't be exact about where they are unless I have an actual function written down that I can manipulate algebraically. We're going to do that in a minute, but let's do a couple more graphs. Just a couple more. Let's say we have this kind of situation here, and then number 6. Oh yeah, that's an annoying example, just a straight line. Okay, so with this one, well, we've got curving up here, we've got a curve up, so this is positive concavity, and then it turns around, starts curving down, so that's negative concavity, meaning somewhere in the middle there's a point of inflection. Now this doesn't have any curve to it at all, so this is kind of a trick example, or a trick problem, because you could kind of argue that all of these points would be points of inflection, because for a linear function, which is what this is, a straight line, its first derivative is a number, right? Its first derivative would just be whatever its slope is. Like if this was like 2x plus 1, then its first derivative would just be 2. But its second derivative, the second derivative of a linear function would always be 0. So its second derivative is 0 everywhere. But I'm supposed to have points of inflection where its second derivative is 0. So that means technically this entire thing is nothing but points of inflection. Kind of a trick example though. Let's just say no concavity. No concavity. And actually there are no, well, without concavity, you can't talk really about points of inflection. Concavity, points of inflection are happening between sign changes in concavity. That's why 2 and 3 didn't have any points of inflection, because there is concavity, but there's no change. It's just positive, just negative. You only have points of inflection when there's a change in sign. Okay. Let's see. Let's do some finding of concavity and points of inflection with some algebra. So I'll call this finding. So given functions defined algebraically now. Finding points of inflection and concavity algebraically. Fairly simple to do it from a picture, you just got to know what you're looking for. But now let's find them algebraically. So number 7 is going to be a cubic function. F of x is equal to x cubed minus 3x plus 1. We want to find second derivative. Set it equal to 0. And solve for x. Or whatever the input variable is. In this case, it's x. First derivative. Got to get the first derivative to get to the second derivative. Whoops. It's going to be 3x squared minus 3 plus 1 goes away. Second derivative is going to be 6x. There we go. 6x. And now we set that equal to 0. 6x equals 0. Solve for x, but that's easy. X is just 0. So the point of inflection is happening at x equals 0. We need to find the y value, the output value of the function at 0. So the original function, because this is a point on the graph. When you're finding a point of inflection, that's a point on the original graph, not the derivative, not the second derivative. You use the second derivative to get the input value for the point of inflection, but the output value needs to come from that original function. So plug 0 into the function. This is fairly easy. 0 cubed minus 3 times 0 plus 1, that's going to be 1. Thank goodness that was pretty easy. So the point of inflection is occurring at 0, 1. 0, 1. Now what about the concavity? Because we know there's a point of inflection there at 0, 1, but we don't have the picture. So is it positive on the left and negative on the right? Well, we have to check around x equals 0. What am I checking? Check around x equals 0. So let's just pick a couple numbers. X equals -1 and x equals 1. Why not? Those are around 0. But what am I going to plug them into? The original, the first derivative, or the second derivative? Well, I'm trying to figure out where the concavity is. Where the concavity is. And concavity is defined by where the sign of the second derivative. So I need to plug these numbers into the second derivative. So f double prime at -1 is going to be -6. I don't really care what it is, I just need to know the sign. And f of 1 is going to be positive. So I've got a negative concavity, positive concavity, so negative concavity on what? What is the domain? Well, -1 is on the left, so I've got negative concavity everywhere to the left of this 0 spot. Okay, and then positive concavity. I could say concave up, concave down. I could say it that way as well. On the right of this x equals 0 spot, so 0 to infinity. And notice I am using parentheses around 0 because I don't have positive concavity at 0. I have 0 concavity at 0, right? That's where the point of inflection is. So these are the, this is the domain, or well, the set of x values where I have negative concavity, and this is the set of x values where I have positive concavity. And it splits at 0. So this graph must look something like, what would this graph look like? It'd be up at 1. So there's the point of inflection, and it's all concave down. It's all concave down. Then it turns around. There's the steepest part in between, and it turns around and goes up. Something like that. There's my negative concavity and my positive concavity, and there's my point of inflection. There's my point of inflection. Okay, number 8. G of x is equal to another polynomial, 2x plus 4 all squared minus 3. This kind of looks like the quadratics that you learned to graph in MS 112 pre-calculus. It looks a little bit different in here, but this would be a parabola. Anyways, alright, G double prime, nope, G prime of x first. Chain rule, right, drop the 2, so it's going to be 2 times 2x plus 4. That's derivative of the outer, so this exponent is now 1. Derivative of the outer with respect to the inner, times the derivative of the inner. What's the derivative of 2x plus 4? It's 2. By the way, the minus 3 disappears because it's constant. So I'm getting 4 times 2x plus 4. Why not? Go ahead and say 8x plus 16. Then, wait a second. Yes, okay. The second derivative then will just be 8. Okay, so I'm supposed to take this and set it equal to 0 and solve, but this cannot be 0 anywhere, because there's no x, right? There's no x, there's no variation allowed. This is a constant second derivative. This is not 0 anywhere. So, we have no points of inflection. You can have points of inflection at undefined spots in your second derivative, but clearly this doesn't have any there's no x for anything to be undefined. It's just an 8. So there are no points of inflection. But we still need to know, is it concave up or concave down? Does it have any behavior like that? But is it concave up or down? How do you tell if it's concave up or down? You look at the sign of the second derivative. But it's an 8. It's always positive. Since g double prime of x is positive for all x, I should say for x in this, right, it's always 8. For any x I plug in, it doesn't matter, it's always going to be positive 8. The graph is always concave up. And that makes sense when you realize that this is a parabola. This parabola would be something like, let's see, down by 3. Where's its x-intercept? Where is, or not its x-intercept, where is its x-coordinate of its vertex? That's going to be where this is 0, so. Okay. Something like this. Parabolic. It's always concave up, right? It's always concave up, and there are no points of inflection. There are no points of inflection, because remember, points of inflection are going to happen where the derivative, where the second derivative changes sign, but this is always positive. There's nowhere where this graph turns around and comes back down, so it's always concave up. And there are no points of inflection. Okay. What about something similar like h of x equals negative x squared? Negative x squared. Well, h prime, so we already know this shape, right? And this is a downward facing parabola. So automatically we're thinking, oh, this is very similar, except it's always a negative concavity, and there are no points of inflection. But let's see if that works out in the algebra. Alright, first derivative is going to be negative 2x. Second derivative will just be negative 2. It's always negative. So, graph is concave down on the entire domain. And there are no, if it's always negative, there's no sign change, right? It can't change signs. There's no x here. It's always negative. There are no points of inflection. Okay. So very similar to the previous example, except it's facing down, so it's got a negative concavity. Or we say it's concave down. Oh, this is an annoying one. You may remember graphing stuff like this from pre-cal. So, this is a polynomial, it's 4th degree, everything's positive, so we know both sides, thinking in the pre-cal terms, just in, like, what does the graph of this look like? Both sides are pointing up, because it's positive and it's 4th degree, and it's got 4 different x-intercepts. One at 1, one at 2, one at negative 1, and one at negative 2. That's where the zeros of this graph are. So it must look something like kind of a W. So it's got an x-intercept. Well, first of all, both sides are facing up. X-intercept at 1, or negative 1 and negative 2 and 1 and 2, so it's got to come down, go through there, and there's no multiplicity. Remember, multiplicity, if it's got exponents, it would have multiplicity, and an even multiplicity means the graph bounces off that x-intercept. Odd multiplicity means it goes through. Anyways, alright, so we go up and go through some y value. To get the y-intercept, we could multiply all these constants together, somewhere up at 4, and then back down through that x-intercept and through that one, and then up. Okay, so if we're really fresh on our pre-cal graphing of high-degree polynomials, then this is all we need, because now we have a picture and we can say, okay, positive concavity here, negative concavity here, positive concavity here, meaning there should be points of inflection right there somewhere and right there somewhere. One in between each sign change in the second derivative, in that concavity. Sign change from plus to minus, so there's got to be a point of inflection there, and then a sign change from minus to plus, so there's got to be a point of inflection there. But let's say you're not fresh on graphing high-degree polynomials, so we got to run through the process of finding that second derivative, setting it equal to 0, etc. Okay. Now, finding the first derivative of this, honestly your best bet is going to be to multiply this function out. In fact, let me do that first and get it as a fourth degree polynomial. So x to fourth, it's going to be, I'll just tell you what it is, minus 5x squared plus 4. Save us all some time. Just plug it into Wolfram Alpha or something. Okay, that's much easier to deal with. It's a nice clean polynomial. Its first derivative will be 4x cubed minus 10x. Its second derivative will be 12x squared minus 10. Now, finally, something that can actually be set equal to 0 and solved for. This is going to yield x is equal to, so take a second, see if you can solve this, and you should get plus or minus square root of 5 over 6. Add the 10 over, divide by 12. 10 over 12 is 5 over 6. And then you take a square root on both sides to get plus or minus square root of 5 over 6. And there are two, plus or minus. There's going to be two. And this is where they occur. What are those points, by the way? So we have points of inflection at negative square root of 5 over 6, comma, whatever that is plugged into the original function, and square root of 5 over 6, comma, whatever that is plugged into the original function. So I'm going to pause and plug that into a calculator. Okay, so the y value at these points of inflection are going to be 0.53, and they're the same because this graph is nice and symmetrical because its x-intercepts are all equidistant from each other. By the way, as a fraction, that's 19 over 36. So there's the 2 points of inflection. Now, where is it concave up and where is it concave down? Because we've got 2 points of inflection, so there's going to be concavity going on to the left of this point, concavity going on in between the 2 points, and then concavity going on the right of this point, which we see from our picture, but remember, we're pretending like we don't have the picture. So let's find all of those concavity signs. So we need to check around x equals negative. We need to check around, or check between rather, and you can make a little table for these and then check, or I shouldn't say around actually, because you say around if you've only got 1 point of inflection, but so we'll say, let me say it this way, check to the left of this negative one, then between the negative and the positive one, and then check to the right of that positive. You can do a nice little table. That's the way I did it in my notes over here. If you see right there, it won't focus. Well, anyways, that's my little table where I have my sine of my second derivative, and then the those 2 points of inflection, and then the number on the left between and right. Okay, so if I check to the left, what's a good number to the left of negative square root of 5 over 6? Well, I can say x equals -1, because that's to the left. It's barely to the left of it, but it is to the left of it. And remember, I'm plugging this into the second derivative. All I want to know is what is the sign of this second derivative at -1. By the way, what was the second derivative? 12x squared minus 10. So 12 times -1 squared minus 10, that is positive, right? It's going to be a positive 12 minus 10, that's positive. So we have concave up here on. Now, to the left of this point, there's no point of inflection to the left, so it just goes off to infinity. And then right up to that point of inflection. Okay, so far this is agreeing with our picture. Okay, now we want to check between these two, but what's a great number between a negative number and a positive number? 0. So f double prime at 0 is going to be 12 times 0 squared minus 10, but that's going to be 0 minus 10, which is -10, which is negative. That's all we care about, right? So it's concave down on. Now, it's concave down between these, between these two. So negative square root of 5 over 6 to positive square root of 5 over 6. Okay. Now, if we want to check something to the right of square root of 5 over 6, just pick one. Why not? It's to the right of it. So f double prime at 1 is going to be 12 times 1 squared minus 10, but that's going to be 12 minus 10, which is positive. So it's concave up on from that point of inflection off to infinity. That's a parentheses, which definitely agrees with our picture here. Positive up to that first point of inflection, negative in between them, and then positive again. And you may notice, you may say, like, well, if it's positive here, it's definitely going to be negative, and that the sign is just always swapping. So once you get one, you can just say, well, if this is positive, then the next one's negative, then the next one's positive. That's not always true. You can have, just like we had, like, imposters for maxima and minima, you can have imposters for points of inflection. You may get points in your graph where the second derivative says, hey, I'm 0 here, but it's not actually a point of inflection. So you should always do this check, because if the sign stays the same, we wouldn't say there wouldn't be a point of inflection there. But since the sign does change between both of these, positive, negative to positive, we do have points of inflection for sure at these 2 points. Okay.